all the equations set here, W, 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 all the W here, this is equivalent charge weight of TNT. If you use something like HB, usually in the school environment, I'm using TNT, okay? Because that's a typical charge. And other charges are, TNT is like a standard, the explosive. Others you can think of deviate from the TNT. Like HBX1 is the most popular charge for like a ship shock testing in US. So which is about 1.5 stronger than the TNT. So if you're going to apply, for example, these equations, any of those equations which involve W, if you want to find the period of the bubble oscillation for when you use the HVX1, then you have to multiply, let's say 100 pound HVX1, then you have to multiply to use this equation by 1.5. You follow me? So I'm going to limit here just the HVX1 and TNT, mostly TNT. But when you see the HVX1, the multiplier is 1.5. Something like 100 pound TNT. The HBX1 is equivalent to 150 pound TNT. Got it? Much stronger. Gusto. Okay? So that's what the equivalent weight is. I think that's, I hope it's all clear. I want to confirm, make sure. But, okay, today I'm going to give you a talk. I'm going to give you a talk on the bulk cavitation. This is one of the phenomena that you must know 100%, 105%. Some area in computation is somewhat confusing. So today, spending for about 40 minutes, 45 minutes, I want to make it very clear to understand. Here, then Friday I'm going to cover the Hopkinson's scaling law and undex relevant. What does it mean, undex? Underwater explosion. Undex the relevant, the very particular scaling law, which is about the only one available for explosion testing. So then that I'm going to spend time to lecture on Friday, okay? Then after I return, then you will get this week, you will get the chapter 10 and the chapter 5. Chapter 10 first. Well, I didn't renumber. So chapter 10 and chapter 5, you will get that this week, today or tomorrow. Then you will get also slowly the mini project. Whenever I say mini project, this is like a weekend project. And usually for mini project, at least the minimum 1 week time. It's not going to take 1 week to complete the mini project. It just may take maybe half a day on the weekend, okay? So that's what we're going to do. So today, the bulk cavitation problem, and also I'm going to assign the mini project. then Higyu, my teaching assistant, will send you by email as attachment the problem set. Okay? And the bulk cavitation, as you see here, bulk cavitation is like white colored water. As you look down from the top of the water, it spread tremendous area, and it's just at the time of explosion, then it spread so quick, even few 100 feet. Then it closes. Then whole explosion process comes up. So the bubbly water, I call sometimes, near the free surface, only occurs near the free surface, okay, which is called the bulk cavitation, is caused by what? What wave? That's such a bubbly water formed up near the free surface, caused by what wave? Tensile or tension wave, or tension wave is equivalent to rarefaction wave, equivalent to surface reflection wave. It's all same, right? It never happened, such a bulk cavitation never happened when you have a rigid surface. When the wave hit the rigid surface, it's going to have a compressive wave. But on the free surface, nothing stops. Water particle can just can kick any direction. Then the bulk cavitation occurs. Bulk cavitation is not like a balloon kind of the things trapped in the water. No, bubble is like a balloon. Inside the balloon there is air, only air. But this bulk cavitation, for the density of the water in that area, in that zone, it drastically coming down, but it's not like a balloon. It's not like air. So another way to say is, if you try, like a tension wave, what does it mean, tension? You try to pull. When you try to pull the water, then cavitation occurs. Remember that. There are two different kinds of cavitation dealing with the underwater explosions. For example, one is bulk. Another type is local cavitation. Some people call hull cavitation. Two different kinds. So I'm dealing with bulk cavitation right now. A local cavitation, if you look at the principle, very easy to understand. Cavitation occurs when you try to pull the water. So here, this is submarine cross sections, okay? And I have a sharp wave comes right in. Could be a plane wave, could be a spherical wave front. Then this is of course a hull. This is flexible, it's not rigid, it's a flexible hull. So when the shock wave, this is a pressure wave, come and hit it, then of course what happened? It's going to cave in, right? It's going to cave in. But it has elastic property, of course. It could have elastoplastic property, but it has a stiffener. It has a flexibility in there. When it hit it, the plate hull will take off, isn't it? Will take off. Right, you know? When this takes off, the velocity of this shell, the hull, the velocity of the shell, if V is, there are water particle right behind the shock wave is all water particle there. When it hit it, then if I say this water particle is U, the local cavitation occurs if the V is larger than U. What does it mean? The shell tried to pull the water, isn't it? Shell tried to pull the water particle. Then cavitation appears around here. When you suddenly try to pull the water, then cavitation occurs in front of the hull. So sometimes people call this kind of the phenomena as hull cavitation or local cavitation. Whenever such a cavitation occurs, shock wave cannot penetrate. Shock wave cannot penetrate in the air. Of course, some will penetrate, but I gave you the example before, you know, in the air-water interface, 1,000 psi shock wave hit the free surface. How much it penetrate into the air? Out of 1,000 Willis, only 0.5 psi. Out of 1,000 psi, only 5.5 psi was able to penetrate into the air. But in this case, it's not really air, but very low density water. So that could affect a little bit. But in other words, 1,000 psi comes right in for the shock wave. It could penetrate more than 0.5 psi, but what I'm saying is it's pretty low. Shock pressure will pass, okay? And bulk cavitation, I want you to read, of course, all this. So bulk cavitation, tensile reflected wave here, which is called the rarefaction wave. So when the cavitation, when the shock wave hit the free surface, the rarefaction wave occurs, then water particles, try to split themselves, then water becomes like a vapor. So the first step is vaporizing. The water is vaporizing, like a steam without temperature. Then that can sustain about 0.3 psi. I usually say 0, okay? 0.3, but some people, as I mentioned, claim that water particle can sustain roughly 5 psi. I said, okay, regardless of what you guys are saying, for my computation to declare the cavitation zone, I'm going to say 0 psi. If the when you look at any point, then you can compute the pressure, shock pressure, total pressure, including the atmospheric pressure plus the hydrostatic pressure. If the total pressure goes 0 or below 0, then you declare cavitation occurs at that point. Okay? And as I said, water cannot sustain the tension. Regardless whether it's a 0.3 for vapor pressure or 5 psi for really the breaking pressure. Breaking pressure really means it's just breaking the molecular level of the water particles. Who cares? Just to set 0 in the computation, that's good enough for the shock calculation. And as I said, read all this nice paragraph. And this is kind of the last chance to understand the tension wave in conjunction with the bulk cavitation. This is a charge. This is a target or gauge, okay? Or point of interest, whatever. Or when I say target, this is like a undersea vehicle location. So I want to see the wave action, and this is absolute pressure versus the time. And at the time of detonation, that's T is equal to 0. So as you look at the incident shock wave, as the charge explodes, then incident shock wave compress the water, and the first wave, incident shock wave, travels this straight path and hit that point, right? This is what you are talking. And initially, before the explosion, everything is under PA, atmospheric pressure, plus PD is up to here, P up to here. That's the interest. The hydrostatic pressure at the beginning. This is right at the target point, okay? This is a pressure history at target point. Everything is all calm here. How long is it going to take from here to here? Up to the point the shock wave hit the target? R over C naught. So R over C naught, the time, I call that usually T1. Remember? T1. T1, this time T1 is R over C naught. Then the incident shock wave hit the target, then it zoom goes up, straight up, even if it has a slight slope as a nanosecond in terms of who cares about nanoseconds, straight up. From here to here is P max. From here to here, P max, dynamic pressure. P max is a function of two parameters. What? W and P max is W and R. You remember that? Remember? You don't have to memorize. I'll give you all the equation, but you have to visualize it. So it goes up. This is this is P max, and if this is absolute pressure, then that target will experience P max. Sometimes I call the P max as equal to P naught. Okay? So then this target will experience PA plus PD plus P max. Total pressure, right? To have a cavitation, bulk cavitation, any point near the free surface. What happened to Sungwon today? Don't know. To have a cavitation, then you have to compute the rarefaction wave. Rarefaction wave, right? So here, rarefaction wave, to do that, you think this as a mirror image, and this is mirror image of this charge. Charge size is usually W, then this guy has still the W image charge. You connect to this, then this is the path which will reflect the free surface and come down and hit the target. And this is compressive wave, and this portion is a tension wave. I talk already at least 3 or 4 times. And all the water particle is attracted by the image charge. Water particle is keep hitting, moving toward the image charge. But as you look at the wave front, which is moving toward the target, is opposite to the direction of water particle. This portion is a tension wave. That's the only chance to have a tension wave, as I recall, for the undexed situations, okay? It's a negative pressure, relieving negative pressure. The water particle is trying to breaking away. Got it? So if I draw, the pressure is a negative pressure from 0. It happens sometimes later. It's called the TC time later. It's called the cutoff time, TC time later. Right? Because this plus that is a longer distance than this distance, right? It takes naturally more time. So how much more time? TC time after. You will see in your midterm exam, you have to compute all this. TC time after. So this is, look at me, this is same as that distance. So this distance plus that distance is same as from here to there, right? So R naught is longer than R. So this distance plus that distance is longer than R. So TC is R naught over C naught. This is a time that T naught comes down to hit the target. Then you have to subtract that distance. Then that's the time that the incident shock wave hit the target. So if you subtract R naught over C naught minus R over C naught, so if you put it together, R naught minus R over C naught is the TC time. Don't forget, even if you understand now, later, I'm warning you, you have a chance to forget. So this is so-called the cutoff time. So if I put just for the the negative pressure due to the tension wave here is P2. So here, when the rarefaction wave is hit that point at Tc, then suddenly, as you look at the measurement, pressure profile is coming down and cut. In reality, you will see the sample case. So this is the reason you have P2 negative pressure initially coming down here, straight down, then slowly goes away. So to see the total change in pressure, it comes up and straight down, then right here it cuts off. Sometimes, depend on the depth, the P2 can be higher. P2 magnitude could be higher than PA plus PD plus P1. Here P1 is not this. P1 here is the pressure, incident shock pressure at the time the rarefaction wave hit the target. Is it clear? It could go below zero, depend on the depth of the target. It could come below zero. When you add this plus that, then what happened? You can draw, okay, comes up, down there, it could go there, it could go like that. But water cannot sustain the tension. Water cannot go below zero for pressure-wise. So even if it goes below up to here, say, no, water cannot sustain the tension, so it has to stop here. So it has to come down, then after this, slowly back up to PA plus PD. Very clear to me, but should be clear to you. You have to know this fact. It costs the 25 point. Very easy to understand, but still chances are there to screw up.
So
Question?
If the target is near the surface, it will feel least pressure. If the target near the surface, it will feel least pressure.
I don't follow you. If the target is near the free surface, it could have the bulk cavitation. If it's deep in the water, it never have a bulk cavitation because it's already hydrostatic pressure is pretty high, so cavitation may not occur. It only occurs near the free surface. So that's the question?
Yeah, I mean, if I look from this graphic,
yeah,
the pressure will be less than this one. The distance is near free surface.
Yeah. Like this point is near the free surface here. How to test out? The P1 plus PA plus PD plus P2, if that's the larger than zero, then what happens? No cavitation occurs. The magnitude, this plus, right here, right at the cutoff. What does it mean, right at the cutoff? The tension wave hit the target. The incident shock wave already passed. So that's what this point is. So this plus that. This is a positive, which means compressive. This is negative, it's a tensile. If this plus that is zero or below zero, then what happened? Then you declare the cavitation occurs. It's coming in next to page. Wait for a while, then read question again. So right at the cutoff, this is right at the cutoff here, right at the cutoff. The chances could have, you could have A or B or C depend on the P2, the tension wave pressure. And the vapor pressure is about 0.3, is around here, just above zero pressure. Compressive, below zero is tensile. So for the cavitation pressure or breaking pressure, which is 304 psi, it just breaks off the molecular level of particle. So what I'm claiming here is this is a detail of the physics. If this right at the cutoff, right at the cutoff time, if the resultant, which is PA plus PD plus P1, then you have a minus P2. If that value goes to, if it's below, goes to below zero, then reset the total pressure at zero, and you declare that point is cavitated. It should be very clear. Sunu, is it clear? Should be clear. So what we do in the mini project, that's what you do the exercise, is due is November 1st, which means you have plenty of time to do all the midterm exam. Then November 1st is a Monday after next week. So the shape is like an umbrella shape. You will see yourself. This shape is axisymmetric, of course. Explosion occurs, right? Charges right there. How to get this? And you have to make yourself grid. Very small interval. Then you don't have to worry about this portion. Why? Because it's axisymmetric when explosion occurs here. So then you have to by the dual loops kind of things, then you have to go through checking every point. Okay, every point is pretty fast in computer PC. Then check it out whether this point is total pressure is below zero or not. Then go through the point. If it goes below zero or equal to zero, then you declare cavitation occurs and not occurs. That's what you have to do. And then it has an exercise problem here. Whenever show exercise, this is homework, okay? Last year I put this in the sheet, then hand out to you. No reason to do that. That's the second year. So this is due whenever I assigned from now on until we finish in December, week later. So today is a Wednesday, so it's going to be Wednesday next week. But you have exam, so Monday, week after next week. November 1st is Monday, which is the day I'll be in class. So just to do it, then bring back on Monday. Is it all clear? Monday, November 1st. So exercise problem. The cavitation calculation, first attempt was done by Dr. Aaron, A-R-O-N, in 1946 or 1949, if you look at the references, his name is there. So then still we are using the same method we call the Aaron's method to compute the cavitation boundary. Okay, to compute the cavitation boundary, Aaron's, okay, A-R-O-N, Aaron's method. That's what the method we are using it. And it has two boundaries. It has charges here. Two boundaries. One is upper cavitation boundary. This is not upper cavitation boundary, not touching the free surface. Why? You have atmospheric pressure. So it should be always below the zero. If this is the 0 point, and the boundary should be just below 0. You will see that in your calculation. This is called upper cavitation boundary. Then there is a lower cavitation. This is exaggerations a little bit, okay? And this is all cavitated zone, which means total pressure, computationally total pressure is equal to 0 or below 0, then that's the cavitation zones. So the Aaron's approach, there are two. This is the first to compute the upper cavitation boundary. Upper cavitation boundary. This is the first boundary you will compute. And then you will compute the lower cavitation boundary. You will compute the lower cavitation boundary using Aaron's method, which I'm going to go through. All the derivation for upper and lower cavitation boundary by the Aaron's method. I gave you my own full derivation in email. You should have. This is straight algebraic. All the details are there. You all received that? You received that. You didn't receive the bulk cavitation derivation? Never received it? Chapter 4, you received it? Never received bulk cavitation, the boundary derivation? Oh, geez, you got it? Let me see. Yeah, that's it. You got it. Then others should get it. Yeah, that's it. Yeah. Gusto has it. But that's so small. Can you read? Wow. Well, you have all that. Suna has it. Jongwon, you have it? Everybody should have it. And that I want you to spend the time and review yourself. Because so detailed, I don't have to do that. Now first, upper cavitation boundary. Upper cavitation boundary, I said what? What's the upper cavitation boundary? You pick any point. Okay, this is subjected. You have to compute the total pressure. Any point in this cavitation zones, total pressure has to be less than or equal to 0 to qualify cavitation zone. to qualify to be the bulk cavitation, total pressure, that point has to be 0 or less than 0. If it's less than 0, you're going to reset, oh, pressure is 0, because water cannot sustain the tension. Then what's the total pressure? PT is equal to PA plus PD, right? Stay there, right? Visualize it. Plus incident shock wave at the time of cutoff. Incident shock wave at the time of cutoff. Does it make sense? Because you are dealing with right at surface cutoff time. You are looking total pressure at the time, then tension wave hit the target. Then incident shock wave is past the P max time, a little bit later. Got it? Then plus P2. Depend on the location. You are considering this, and that. You end up to compare. If this guy is higher than this, then what happened? Total pressure goes below 0, which means cavitated. If this guy is higher than that guy, then what happened? Water does not cavitate. Still incompressive, isn't it? So you have to compare this 1 and 2. So you have to compare if 1 is larger than 2, no cavitation. If 1 is equal to 2, then what happened? Louder. Cavitation occurs. If 1 is like this, what happened? Cavitation occurs. This is very important. And of course, this relation is true any point within this zone, whether it's lower cavitation boundary or upper cavitation boundary. This is all true, nothing but true. But Aaron's saying, very easy to find using this for upper cavitation boundary, but not that easy for lower cavitation boundary. So he proposed this approach. So I'm going to read this yellow, defining the breaking pressure as the rarefaction wave pressure, which reduced the absolute pressure at the point to the cavitation pressure, which means it's really 0. In other words, the breaking pressure means it's really tensile, the wave. As that wave hit different point in the water, then if the breaking pressure is getting over to that absolute pressure in the water, then you declare it's cavitated. However, that's the definition for breaking pressure. Here, to capture the lower cavitation boundary, it deals with the decay rate of the breaking pressure. Decay rate of the breaking pressure, which is really for tensile pressure, the rate of change along the given direction, has to be right at the the boundary, lower cavitation boundary in this case, the decay rate has to be the same right at the boundary for the absolute pressure, because you keep relieve the absolute pressure, tensile pressure, relieve absolute pressure. Then when the rate of change in the radial direction is the same, then what happened? Then that's the point that cavitation occurs, okay? You have ample, the write-up in the separate file, and as you see there, then you can see it generate solving this equation set and doing so on. I'll continue this on Friday, okay, Friday morning.